Biorefinery System Module 9 Lignocellulose Biorefinery Product Engineering Segment 2 Bioenergy with me Yusuf from Bioengineering Study Program School of Life Sciences and Technology Institut Teknologi Bandung. Previously, we have discussed about the overview of lignocellulose biorefinery product engineering. In this segment, we will discuss about bioenergy. Solar energy is the source of almost all energy on Earth. Biomass is a resource produced from the conversion of solar energy. Conversion of biomass to bioenergy alternatives of coal, oil and natural gas or other fossil is following the mass cycle with a theoretically zero net carbon dioxide emission as shown in the right figure. Alternative energy can reduce carbon dioxide emission through improving the energy utilization methods and the utilization ratio. The ultimate aim of bioenergy research is to reduce our dependence on oil, thus our current challenge is to search for large-scale economically visible bioenergy technologies. In order to realize the internalization of bioenergy, two key factors are essentials. First is the determination and planning of government favorable legal policy, guaranteed huge investment and market demand from consumers. And second is making constant progress in biorefinery technologies and breakthroughs in key technology. Using different techniques, biomass can be converted into different products. Therefore, with the development of raw material resources, biomass energy, and advances technology, biomass energy will play an important role and indispensable role in human life. The most direct and important application for the bioenergy system is to produce ethanol through biomass fermentation technology. Ethanol is a new kind of green energy as well as a basic chemical raw material that is widely used in the chemical engineering, food, beverage, military, household chemicals, pharmaceuticals, and health fields. As an excellent fuel, ethanol can improve food quality and offers various advantages. More than 90% of the ethanol in the world is produced by fermentation of biomass, so ethanol is a renewable energy source. Among the main materials to produce fuel ethanol are sugar and starch, but since they are edible, the production of ethanol from these materials faces the problem of competing for a resource that is a source of food for humans, and the cost of raw materials makes up more than 40% of the total cost. Other raw materials are corn stalks, and the process flow chart of fuel ethanol production from corn stalk is shown in the right figure. Lignocellulosic raw materials like straw also can be used to produce fuel ethanol because they are abundant, but their complex structure requires complicated technology routes and results in low utilization rates and high energy consumption for separation, which leads to higher production costs than sugar and starchy materials. To fully use the lignocellulosic raw materials, the following changes must be overcome. Technology must be simplified, production costs must be reduced, and wastewater emissions must be reduced. Biobutanol is a second-generation alcoholic fuel with a higher energy density and lower volatility compared to ethanol, which is more suitable for the existing fuel supply and distribution systems. Butanol is an important chemical raw material and organic solvent, which is widely used in industry, medicine, and food. At the same time, butanol is more environmentally friendly when compared to fuels from oil refining and hence decreases the emission of greenhouse gases during the gasoline refining process. Corn, wheat, and molasses have been the primary materials for acetone butanol fermentation for a long time. The flowchart of converting hemicellulose into butanol and the comprehensive utilization of corn stover is shown in the right figure. Raw material costs account for 60 to 70% of the total cost of butanol, which is an important limitation of the industrial development of butanol fermentation. Lignocellulosic biomass is also a potential resource for reducing the production costs. Since the composition of lignocellulosic feedstock materials is more complex than food and the conversion efficiency is relatively low, lignocellulosic raw materials should be pretreated before fermentation. The bottleneck for butanol production lies in the low butanol concentration caused by the inhibition of butanol fermentation products. Therefore, it is necessary to adopt a strategy of continuous fermentation to achieve efficient production of butanol and the aim of coupling fermentation with separation technologies. Marsh gas is one kind of renewable resource and using waste from marsh gas production by anaerobic digestion. The effective component of marsh gas and natural gas is methane, and the content of methane in purified marsh gas could reach 95%. Biogas can decrease energy consumption, reduce pollution, and construct a platform of rural energy conservation and emission reduction, as well as improving rural health, solving the problem of household energy consumption of farmers, and protecting the environment. Producing biogas from straw has the advantages of abundant materials and wide distribution without limitations of time and space, which can achieve a complete ecological cycle and effective utilization of straw. Straw is rich in cellulose, hemicellulose, and lignin that contain plentiful energy. Therefore, straw can be used as a potential energy supplier to solve the current security issues related to the energy supply. Through appropriate pre-treatment, bioenergy in the form of biogas could partly satisfy the need of renewable green energy. In this way, biogas not only solves the problems of agricultural waste, pollution of the environment, and the disposal difficulties, but also produces biological natural gas that partly displaces fossil resources. Hydrogen itself is renewable and zero release because it does not generate any kind of pollutants, even carbon dioxide, during combustion. The energy density of hydrogen is 2.68 times higher than that of gasoline. Its thermal efficiency is 30 to 60% higher than that of other fossil fuels when converted to power. In addition, hydrogen can serve as fuel for engines directly. At present, hydrogen is used as an alternative to fossil fuels in hydrogen fuel automobiles and hydrogen fuel cells. However, it will not meet the need for sustainable development over the long haul. High cost is the main problem restricting the industrialization of hydrogen production. Dark fermentation coupled with biohydrogen production technology could integrate effluent treatment, solar energy utilization, and clean energy production organically and form a new kind of environmentally friendly industry. However, future research is needed on both dark fermentation and light fermentation for hydrogen production from industrial and agricultural wastewater, municipal sewage, livestock wastewater, and lignocellulose biomass materials, which could decrease production costs and help protect the environment at the same time. Combustion properties were increased by 20% after the biomass was molded into solid briquettes. Moreover, the emission of greenhouse gases are lower than coal. Biomass briquettes have the advantages of an abundant supply of raw materials, simple technology, convenient operation, and low cost, hence fits for utilization on a large scale. Biomass briquettes are produced through dehydration of collect loose straw, then grinding and extruding the straws into rod-like and granular ones as shown in the right figure. Biomass briquettes solve the problems of low bulk density, low energy density, and difficulty of storage and transfer. However, the main problems of biomass briquettes utilization are hearth corrosion and slag bonding. Hence, further modification is required. There are several commercial values for bio-oil that needs to be highlighted. First, bio-oil can completely dissolve in alcohol. Second, bio-oil is insoluble in diesel oil, although it could be emulsified by diesel oil. Third, the quality of bio-oil can be improved through catalytic reforming, which is similar to that of petroleum. Bio-oil can be gasified or converted into manufactured gas, biodiesel, or biomethane. There are several problems in the application of bio-oil, such as high oxygen content, 35 to 40%, high corrosivity ability, poor thermal stability, high viscosity, and low calorific value. Such properties restrict the application of bio-oil as an engine fuel. Moreover, due to the high oxygen content, bio-oil is easily hardened on contact with air. Therefore, only after refining could bio-oil have the potential to partially displace fossil fuels and be used in existing thermal equipment, especially in internal combustion engines. For the next segment, we will discuss about bio-based chemicals. Until then, I am Yusuf from Institut Teknologi Bandung.